24 more hours.
This is eye over certain area.
I really hope we don't do this. That's
All
like the only thing I can
figured it out. It's a specific area, so I'm trying to find the specific.
Yeah, that would be like.
We did it before with like the Sigma equals like.
So it's always watch.
No, it's high area.
Yeah.
Okay.
So you can't walk.
For some reason, I did not have that. Yeah, like I understood this one.
You didn't do it like that. No, you just, no. You didn't do it. It's the same thing if you try to pass.
I'm checking it off the wall. I might, Wednesday, I could play games with him, so I can play you.
Yeah.
Wait, so this is tournament, but not you?
Yeah, last one.
Which one are you auditing? Are you auditing?
I want to stay this. You don't have to. I'm scared because edit this out. Basically, I'm doing it now, so I don't have to do it later.
But couldn't you just make the credit for your different?
You said it's just.
You could, but I would still have to take, I would still have to take the credit perfectly.
Is that?
Glasses, man.
It's supposed to be that. Oh, so you wanna like, if you go to UT, everyone's still right?
Oh.
Yeah.
Thinking of my child.
Cal looks like Travis.
Yeah, my phone call. I had fun doing that.
What's your phone call?
Drake just gets me sick.
He called me and said, forget what my dad was on.
French movie restaurant.
I think I'm gonna have to erase my notes on this page.
I actually thought of it. He's actually
I thought this is.
He really talks about himself.
Making the audit.
Mr. Martin. No, dissect podcast.
You guys do this right here?
You know, there
I
put grapes.
What?
That's what we will be grape in Italian.
Oh.
Really?
You said 0 words. Maybe a lot of.
Wait, get your application.
If you said it, we're not allowed.
Yeah, definitely. Except somehow it did.
No,
Oh, I guess it was on Johnny, but he was in.
Jackson, you did not finish it for the other guy. I was like,
Yeah.
I was like, hey, Jackson.
For my army or something like that.
I just like picture my.
It was funny when you were there. No, it wasn't.
But I definitely.
You actually like the dumb shit.
Grab and I. That's something.
I was like, wait.
That was so.
That was one time.
Yeah, what's that to you? Just bio?
I'm literally putting numbers in
Yeah.
a spreadsheet. It's like, I don't need to take.
Other ones are too high.
To say like.
Okay.
Say numbers to yourself. Exactly. What do you mean?
Yeah.
That's what-
That's what he's passionate.
You're passionate about it, so.
I don't know if that was a minute late. Last period, they were like, they made no sense.
No, they're on
Oh,
Yeah, that was the first bell, and we're about to get like.
That was
the first one.
7 minutes from now.
that was the ending bell for second period.
7
yeah.
minutes from now, we'll get a morning bell, and then 3 minutes after that, we'll get.
Yeah, you're totally right. Because 10:46 was when second should have ended on a stop break day.
Can they just like?
But the thought rate day, why would it be on that? We've had several days since then.
That was funny.
Oh, because it's Wednesday. It's Wednesday, which was the thought break game. It's like they didn't fix the. That is a good guess. Okay. All right, guys. All right, we have our very last lesson today. So after you finish kind of your last assignment, your last MATLAB, and your last test, we are doing all of our lasts in the next week or so. Our only project this year normally would have been our last project, but this time is the only. So yeah, we're gonna finish it up today. Then be done. And yeah, that's it. So today we're looking at what's called singular value decomposition. This is used in a lot of compression, data compression stuff. So if you look at how images are compressed, this is one method. There's not obviously other ways they can do it. But so if you took like an image that was really high resolution, could be blown up really large and be really sharp. You might not need that. Like if you're just having a website, you don't want it to load an image that's, you know, hundreds of megabytes of information. You just need a little thumbnail. Singular value decomposition is one way to remove a lot of pixels that will still leave the original image intact. It will just be lower resolution. So if you tried to blow it up, it would be very pixelated, but as a small image, it would work. So singular value decomposition is one way to do that. It's used in like signal processing, large amounts of data, compression, stuff like that. So basically what we're going to see is it's very closely related to our diagonalization of a matrix. It's just that with diagonalization, we can only do that to square invertible matrices. Singular value decomposition, we can do to any matrix, rectangular, not invertible, all sorts of different types of matrices, which is convenient because again, like with image processing, not all images are square, in which case you couldn't really diagonalize the matrix that goes with the pixel density of a square matrix or whatever. And it's all based on orthonormal bases for the 4 subspaces. So this, some of this stuff is review, but from a while back. But as we do this, what you are hopefully going to see is it's very closely related to our diagonalization of square invertible matrices. It'll be a little bit different because we can do this to other types as well. But we'll get this kind of diagonal matrix that's very similar to our lambda. And then we'll have 2 different kind of matrices here as well. So this will work on any m by n matrix. Rank R, rank being the number of pivots, rank being the number of vectors in a basis for the row space and the column space. If A is rectangular, we can't find eigenvalues into eigenvectors. Those only exist for square matrices. And then typically what's very useful is in symmetric matrices, we saw they had orthogonal eigenvectors. So even when we diagonalized symmetric matrices, we could go a step further and diagonalize because they have orthogonal eigenvectors. We could make those orthonormal by just dividing by the magnitude. And instead of doing this S lambda S inverse, we could do Q lambda QT because with orthonormal columns, the inverse is a lot easier to find. But none of this will work for, again, non-invertible matrices or not non-square matrices. So instead of finding eigenvectors and eigenvalues, we're going to find what are called singular values and singular vectors that have some stuff in common, but are not quite the same thing. Okay, so we'll have this m by n matrix, rank R, which means we'll come up with a orthonormal basis for the different subspaces. The column space will have R vectors. That's what rank tells us. There's R vectors in the column space. We'll use an orthonormal basis for the column space. Okay, and those ones we're going to call U. So in our formulas, those are the U's. So we'll have R of these U's. Okay, it's a subspace of Rm. Then we'll have V's. V's will be basis vectors for the row space. There will also be R of them, right? Because the basis of the dimension of the row space is also equal to the rank. So we'll have R of these V's that are a subspace of Rn. And then if you look back at when we first talked about the four subspaces, the column space and the left null space are orthogonal to each other. And when we put their basis vectors together, we get a basis for all of Rn. So we will load the left null space vectors, basis vectors, in also to U. We'll just pick up where we left off. So if we had RUs, we'll start at R plus 1, and we'll get all the way to M of them, and put them all in a matrix that we call capital U. Okay, it's got column vectors, left null space vectors. The column vectors are all going to be orthogonal to each other because we'll have come up with an orthonormal basis there. The left null space vectors will also be orthogonal because the left null space is orthogonal to the column space. Okay, that was one of the kind of the main fundamental ideas when we talked about the subspaces. Okay, with the V's, along with those row space vectors, we'll put in the null space basis vectors. Again, same idea. They're already perpendicular to each other because that is one of the fundamental ideas of these subspaces, is the row space is orthogonal to the null space, right? When I take any row vector times a null space vector, I'm going to get 0. That is what we're literally looking for when we find the null space. And then I'll do the same thing. I stopped at R, row space vectors, and I'll just pick up there and get all the way to N total vectors in V. Okay, and then we'll call that vector, that matrix V. These are the definitions of these things. This isn't actually how we're going to find them. Okay, this would actually be a pretty difficult thing to find. We would find our basis vectors, but then we would have to do something like the Graham-Schmidt process, which probably a lot of you don't remember, but if you look back at your notes, to make an orthonormal basis, we would use something like Graham-Schmidt process to do that. And it would be kind of a lot of steps, a lot of work. Okay, by definition, this is what it is. This is not how we are going to find it. But this is what we'll end up with when we get our U and our V. Okay, so the vectors will be chosen that for any I, A times my V vectors should give me sigma times a U vector. So some vector, like vector 1 out of V, should be a constant multiple of A times that V vector. So sigma, this is a constant. Here. So again, you should be seeing similarities here to like A times X sub I equals lambda I times X sub I from the eigenvectors. Okay. When I did A times an eigenvector, I get a multiple of that eigenvector. Here, when I do A times a vector from V, I get a multiple of a vector from U. So it's a little bit different in that I'm not getting a multiple of the same thing. These are not eigenvectors, eigenvalues. But this time when I take A times a V1, I'll get a multiple of U1. When I take A times V2, I should get a multiple of U2. So instead of doing them individually, we put them in as a matrix, so I can do all of them. So A times this capital V is equal to U times these sigmas. The sigmas we just put in as a diagonal matrix of constants, just like we would with the capital lambda from diagonalizing. So if you looked back at your notes from diagonalizing, this is where we started with diagonalizing the matrix. Is A times our eigenvector matrix is equal to a constant multiple of our eigenvector matrix. Here, A times V will be a constant multiple of our U matrix. So again, a little bit different, But same idea, this was a diagonal matrix just like this was. Okay, and since the columns of V are orthonormal, we can use V transpose as its inverse, right? V times VT should give me the identity. Since they're orthonormal columns, any vector times itself will give me 1, since they're unit vectors. Any vector times a different one will give me 0, since they're orthogonal to each other. So when I take like V1 times V1, I'll get 1. V2 times V2, I'll get 1. V3 times V3, I'll get 1. Those are the ones on the diagonal of the identity. But when I take something like V1 times V2, I'll get 0. V1 times V3, I'll get 0. V2 times V1, I'll get 0. Those are all the zeros in the identity matrix. So we can take this A times B equals U times sigma, and we just multiply both sides by V transpose. This kind of gets canceled out, and this is called the singular value decomposition. Again, very similar to when we did A equals S lambda S inverse, or even more when we did it for symmetric matrices, it was A equals Q lambda Q transpose. Because in symmetric matrices, the eigenvectors are orthogonal. So our S we could make into a Q, an orthonormal matrix, because the vectors were already orthogonal to each other. So again, notice these are very similar. We'll have a matrix and a transpose and a diagonal, and here's a matrix and a transpose and a diagonal. The difference here is Q is the same thing when we're diagonalizing. Here, U and V are not the same. Okay, but there is a constant multiple relationship between them, but they're not the same as each other. Okay, so that'll be called our singular value decomposition. So then it just becomes, where do we get the V's and the U's from? Okay, again, we could technically find basis of a column space, the row space, the null space, left null space, use Graham-Schmidt to find an orthonormal basis, try and kind of piece it together that way. That would be really tough, a lot of work, kind of like by definition, I guess that's the way you do it. But here instead, we're going to look for a different relationship that we can use. So we have A equals U sigma V transpose. And we're going to look at what would A transpose then be. So if I took U sigma V transpose and then I transpose that whole thing. Again, if you look back at your notes pretty far back, if we take the transpose of a bunch of matrix being multiplied, it's the same as the transpose of the individual ones multiplied in the opposite order. So here, V transpose transpose. So if we take a matrix, we transpose it, and then we transpose it again. That just is V. Sigma transpose, sigma is a diagonal matrix. It's symmetric. So when I transpose sigma, nothing changes. So that'll just be sigma. And then U transpose would be U transpose. And so what we're going to use is A transpose A, then will be V sigma U transpose times U sigma V transpose. Remember that U and V both have orthonormal columns. So U transpose U is just the identity. That's going to cancel out. And so we're going to end up with V sigma times sigma, so sigma squared, times V transpose. Okay, remember A is square, symmetric, invertible, which means what we've really got here, this is the diagonalization of A transpose A. Which means our V's are the eigenvectors of A transpose A. So that's how we're going to find the V's, is this is like sigma, lambda, sigma well, I guess since it's symmetric, these are Qs. And then our sigmas, notice our lambda is sigma squared. So our sigmas are the square root of the eigenvalues of ATA. So that's how we'll actually find the V's and the sigmas is we'll do ATA and then do what we've been doing now since before the last test is find eigenvalues, find eigenvectors. And those will basically be what we're looking for here. For the U's, technically we could do the opposite. A times A transpose, also square, also symmetric. And if we did the same thing, what we'd see is this is U sigma squared U transpose, which is the diagonalization of AAT, which is symmetric square. So your U's would be the eigenvectors of AAT. But there's actually a shortcut. This method will work. You could do it that way. You could do ATA, find its eigenvalues and eigenvectors. AAT, what's nice is the eigenvalues are the same for AAT and ATA. It's just the eigenvectors will be different. So find the eigenvectors. We can kind of skip that second step of having to redo eigenvectors for a different matrix because there's actually a shortcut. Once we know sigma and we know V, we can find U a different way since A times VI should be sigma times UI. That's it. Sigma is just a constant. So if I know sigma, divide by sigma. And if I know VI, just multiply by A. And that'll give me each of my U's. So once I've already found sigma and V, I do AV, divide by sigma, and there's each of my U's. And this is fine as long as sigma is not 0, right? If we have any eigenvalues of 0, we'll have sigmas of 0, in which case this shortcut won't work. But I'll show you an example where you get that. You usually can still figure it out. If you can find the other U's, remember they are all orthogonal to each other. So if I have like 2 of the 3 U's, I just have to figure out what's the one thing that would be orthogonal to these other 2. So you could still kind of figure it out even if you get a lambda of 1.
And that would just be a cross product, right?
You could do a cross product, and often you can just look at it. You can kind of figure it out. But yeah, you could do a cross product and find it. A lot of ours will be simple enough that you're like, oh, I have 1, 0, 0, 0, 1, 0. What would the other one be? Or something like that. Or if you're only doing 2 of them, if I have like 1, 1, perpendicular to that would be 1, negative 1. So a lot of times you could just kind of look at it. But yeah. So I'll show you an example of what I mean there. But if you get a sigma of 0, find the other ones and then just use those to say, oh, this is perpendicular to these other things. Okay, and that's basically it. So we're going to go through 2 examples to kind of see how this works. Mostly, this is all very similar to what we've been doing. You're basically going to find eigenvalues and eigenvectors. So here, we're going to find the singular value decomposition. So we're going to need A transpose. So that we could get A transpose A. That's 9 plus 16 is 25. 0 plus 20 is 20. 0 plus 20 is 20. And then 0 plus 25 is 25. Okay, at this step, you should have a symmetric square invertible matrix. If it is not symmetric, right away, something has gone wrong. Okay, this should end up symmetric. All the stuff in this is based on that happening. If it's not symmetric, there's a problem. You've added wrong or multiplied wrong or something. So go back and look at that. Then we're just going to find the eigenvalues and eigenvectors of ATA like you would normally in any of the stuff that we've done up to this point. So 25 minus lambda, 20, 20, 25 minus lambda. So here we get 625 minus 50 lambda plus lambda squared minus 400 equals 0. Okay, larger numbers than we typically have seen, but this factors. Okay, you'll have lambda squared minus a 50 lambda plus a 225. It's lambda minus 5 and lambda minus 45. So we have our two eigenvalues for ATA 5 and 45. These are our sigma squared. It's like sigma 1 is the square root of 5. Sigma 2 is the square root of 45, which is 9 times 5, which would then be 3 square root of 5. Okay, so that's one of our three matrices we're looking for. Those are our sigmas that we need. The other ones come from the eigenvectors of this same matrix. Use the lambdas, not the sigmas. Okay, we're finding eigenvectors. Don't use the sigmas. Those are just going to be used later. So subtract 5, I get 20, 20, 20, 20 times x1 equals 0, which means x1 is 1, negative 1. All we need to do to find v's is it needs to be a unit vector. So we take that same thing, and our first v is just the unit vector parallel to that. So 1 over square root of 2 times 1, negative 1. Okay, that's our v1. Technically, v2, I already know it's perpendicular to that. 1 over square root of 2, 1, 1 would be perpendicular. So you could just do that. Okay, that's going to be what we're going to find. Or you could find the other eigenvector. So if you didn't see that, or you don't kind of get what's happening there, just solve for the other one. So subtract 45, and we have negative 20, 20, 20, negative 20 times x2 equals 0, which means x2 is 1, 1. Which notice they should come out orthogonal since it's symmetric. ATA is symmetric. It has orthogonal eigenvectors. Again, if that's not perpendicular to the first, which it is, problem. Okay, v2 is just the unit vector version. So 1 over square root of 2, 1, 1. And so there's lots of places where you kind of see if these are not perpendicular, some mistake has happened because they should come out perpendicular. So that is your matrix V. We have sigmas, we have our V's. For U, again, we could do AAT. We already know the eigenvalues because they'll be the same, and we could find the eigenvectors, or we could use that U1 is 1 over sigma, so 1 over the square root of 5, times A, which is 3045, times V1, which is 1 over square root of 2, 1, negative 1. Okay, multiply that all together, we'll have 1 over square root of 10, 3, negative 1. And again, U2 is perpendicular to that. So it's going to be 1 over square root of 10, 1, 3. You can just jump straight there if that makes sense to you. Otherwise, you just do the same thing. So 1 over 3 root 5 times A times V2, which is 1 over 3 root 10 times 3, 9, which I can cancel the 3's there, and that's 1 over root 10, 1, 3. Okay, which is what, again, I would be expecting to see. And I'm fine with you actually not doing the second one and saying, I know what's perpendicular to 3, negative 1, it's 1, 3. And that should be the case that's happening here. And so then there is your 3 parts that we need. Okay, A equals U. So 1 over square root of 10. And then just put those in as columns, 3, -1, and 1, 3. Sigma is just a diagonal matrix with the sigmas on the diagonal. So square root of 5 and 3 square root of 5. Zeros everywhere else. And then V transpose. So I'll have 1 over square root of 2. This time you'd put them in as rows because that part's transposed. Okay, and you don't really have to do much. I might multiply the 1 over square root of 2 and 1 over square root of 10, 1 over square root of 20, so 1 over 2 root 5. And notice, that technically you could kind of do some simplifying here. I'm fine with you just leaving it like that. Okay, that is the singular value decomposition. And again, it should look similar to when we did diagonalization. You have this diagonal matrix here in the middle, and then you have these other two matrices out on the sides being multiplied. The difference is these times those are not inverses of each other. Yeah, you can do this with a rectangular matrix as well. So here's a rectangular one. So here I chose a pretty simple one because it's going to make it larger, which is going to make obviously the eigenvector, eigenvalue steps more difficult. But this one I chose a pretty easy one to do all that on, just to kind of give a good example. So we're going to get the transpose. And then we'll multiply AT times A. First row times every column will be 0. Since my first row of AT is 0. So I'll have 0, 0, 0. Second row times the first column is 0, but then the second row times the second column is 1, then 0, 0. Third row is going to give me a 0 and a 0, then a 4 and a 0. And then the fourth row, 0, 0, 0, 9. Okay, so I chose one. This should be pretty easy to find eigenvectors and eigenvalues of. Typically, a 4x4 would not. So if you end up with a 4x4 on a homework or a test, make sure you're looking. This should be something that is very simple in terms of eigenvalues, eigenvectors. You shouldn't be having to solve like a fourth order polynomial by hand to try and figure out eigenvectors and eigenvalues. Okay, here it's a diagonal matrix, which means the eigenvalues are just the diagonal entries. So 0, 1, 4, and 9. Okay, because it's diagonal, we can just use those entries, which means our sigmas are just the square roots of those. Square root of 0 is 0. Square root of 1 is 1. Square root of 4 is 2. Square root of 9 is 3. Okay, there's our sigma. So again, we've got our sigma matrix. Then we just subtract the eigenvalues along the main diagonal. For this first one, it won't do anything, right? Because it's zeros. So we're just looking for where that thing would be 0. Okay, zeros everywhere else. And on a lot of these, I'm probably not going to write all the zeros because it's very repetitive here. But we're looking for what I would multiply by this matrix to get 0. And hopefully what you would see is first column is all zeros, which means my first element of x1 could be anything. And then I just make everything else zeros. Basically, my free variable is that first column, so make it a 1. And then you'd see everything else would just be zeros. You could technically make it whatever you want. I would pick 1 since ultimately we want a unit vector. This will already be a unit vector. This is V1. Okay, then I subtract 1 along the main diagonal and I do the same thing. So I'll have a -1, a 0, a 3, and an 8. Zeros everywhere else. So there's going to be a pattern going on here. This time my second column is all zeros, which means my second element of x2 could be anything. I'm making it a 1. This is just v2. Okay, if it wasn't already a unit vector, you want to make it a unit vector. So I'm not dividing by the magnitude because all of these have a magnitude of 1. Subtract 4. I have -4, -3, 0, 5. This time, third column is all zeros. So 0, 0, 1, 0. This is my v3. And again, at this point, you don't really have to do the other one. X1, X2, X3, and X4, or V1, sorry, V1, V2, V3, V4 should all be perpendicular. I have 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0. What's the other one that would be perpendicular? We could just say, I know it's going to be 0, 0, 0, 1. Or again, you could solve the fourth one, but that's what I kind of mean by you could just pick the other one that would be orthogonal. Yeah.
Would both all the x's be perpendicular and all of these be perpendicular because it's symmetric?
Yeah, the x's should all be perpendicular as well. They just may or may not be unit vectors. But yeah, since the A transpose A was symmetric, your x's would all be perpendicular as well. Yeah. Okay, now so we have our v's, we have our sigmas. For our u's, we can use our shortcut other than on that first one. So this is an example. Sigma is 0, so I can't do 1/0 times a v1. But I would just go ahead and find the other ones instead. So u2 is 1/1 times a 0, 1, 0, 0, 0, 2, 0, 0, 0, 0, 3. And when using the shortcut, because we're going to need 4 u's, and we're only going to end up with 3 if we use this. When using the shortcut, I would go ahead and just add rows of zeros until it's square. Okay, this isn't changing really like the column space, the row space, stuff like that. It's going to make it so that the shortcut gives you the right number of u's that we kind of want. So I would just add a row of zeros. So I have 1/sigma times a times v2. And that'll give me 1, 0, 0, 0. U3, 1/sigma, what was sigma 2? 1/2 times a times v3. So I'm not going to rewrite a. We're using that exact same matrix. This time when I multiply, row 1 times my v3 will be 0. Row 2 times v3 will be 2. Row 3 will be 0, and row 4 will be 0. So 1/2 of 0, 2, 0, 0 is 0, 1, 0, 0. Okay, U4, 1/sigma times a times v4 will be 1/3. Row 1 of a times v1 will be 0. Row 2 times v4 will be 0. Row 3 times v4 will be 3, and then 0, and so we'll have 0, 0, 1, 0. And so this is kind of what I mean by finding U1. Notice that we have U2, U3, U4. I just need what's orthogonal to those. So I have 1, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0. So this is going to be 0, 0, 0, 1. Right, just pick the thing that's orthogonal. And we're not going to do stuff that's like super complex. You probably will be able to just kind of look at it and figure out what's orthogonal. So then A equals U, 0, 0, 0, 1, 1, 0, 0, 0, 0, 1, 0, 0, sorry, 0, 0, 1, 0. Sigma is 0, 1, 2, 3 on the main diagonal of a diagonal matrix. And then V transpose, I put in my V's as rows, although doesn't matter because it's the identity anyway on this one. So I picked a pretty simple one to start with, which is why it looks pretty simplistic there with all the ones and zeros of this. Well, a lot of my zeros don't look so good. Sorry about that. Zero, zero, zero. Ta-da! That is it. Ooh. Knocked all my stuff off my desk here. All right, so that's all for what we're going to cover in linear algebra. We again have some kind of final grades to wrap up: test, MATLAB, problem set, project. But otherwise, no more new information. That's all of it. If you guys need anything, let me know. Otherwise, tomorrow we don't have any class of any sort, and I'm not really leaving any extra work. You guys have a problem set you could work on if you really need something to do. Don't forget to check in with your 7th period tomorrow. That's the attendance period. You don't have to check in with any other classes, but your 7th period teacher should be telling you how you check in for attendance. And then I'll see you guys on Friday.